Hi there, folks. Today we're looking at this thing called Cramer's rule. And this is just another way to solve systems of equations by matrices. And we're going to use this thing from the matrix called the determinant. It's a value we calculate from the matrices that hold certain properties about matrices and about these systems of equations. And we're going to use this thing called Cramer's rule along with these determinants in order to solve systems of equations. Okay. And so the first thing we need to look at here is, well, what is a determinant? How do we find the determinant of a matrix? And so when I have a matrix, there's two ways to denote that we want the determinant. We either put this DET out in front of this thing. That means determinant of this matrix. Okay. Or another way to list that is, instead of using our brackets around this thing, we just use these bars. When we see just bars, they almost look like absolute value symbols. When we see just those bars around a matrix, it means I want the determinant of that matrix, okay? And either one of those notations is an acceptable way to say, hey, I want the determinant of this thing, all right? When we find the determinant of a matrix, it's essentially a combination of multiplying the diagonals and then find the sum of the downward diagonals, the sum of the upward diagonals, and add them together. A 2x2 matrix like this is a little bit unique in terms of the way we find the determinant, in that we just do the two diagonals and then subtract them. And so here we do the downward diagonal multiplied together. That's what gives me this guy right here, the AD. And then the upward diagonals multiplied together. All right, that gives me this. And then I subtract the two. Sorry, you can't really see that. That's not a great way to denote that, okay? And so again, it's just upward diagonals and downward diagonals, and then we subtract them, okay? And so when we look at something like this guy, again, I'm going to do the downward diagonal here, the 1 times the 5, and when I do 1 times the 5, that gives me a 5. And then I do the upward diagonals, that's 2 times the 3, that gives me a 6. And then I simply subtract these two things. And when I subtract those two things, it gives me a -1. Okay, so that is my determinant. It's just the downward diagonals and the upward diagonals. We multiply out those diagonals and we subtract them. Okay, likewise, when I look at this one, again, the downward diagonal here is 1 times the 4. That gives me a 4. The upward diagonals is -2 times the +2, which is a -4. And I want to subtract these things. So again, I'm subtracting. So be really careful with your signs here. That ends up giving me a +8, because 4 minus a -4 is a +8. Okay. When we look at a 3x3 matrix, this is a little bit more like what determinants normally give us. Okay. When I look at something like this guy, again, I have to do each set of downward diagonals. And so like here, like this first downward diagonal is these 3 values multiplied. The next step would start with this B, and as I go diagonally, I kind of run out of space, and when I hit this wall, I have to pop out at the same spot on the other side to continue that diagonal. And so that second diagonal is the B times the F times the G over the other side. Likewise, when I do this C, as soon as I hit this wall, I pop out at exactly the same spot on the other side to continue my diagonal. So that third diagonal is C times D times H. Okay, and one of the things that we do to make this easier on ourselves is we simply just rewrite these columns. So like if I'm rewriting this guy right here, I just start rewriting the matrix over again off to the side. That's just a nice little trick that allows me to see these diagonals a little bit more clearly. Okay, now I can see those 3 downward diagonals very clearly without having to hop around each side of the matrix. Likewise, the upward diagonals are a lot easier to see when I have it written this way. I can see all 3 of those upward diagonals very easily now by writing that out, okay? And so again, when we do the downward diagonals, we're still doing the multiplication. Let me get rid of all that extra stuff. And so when I do these downward diagonals, again, it's multiplication. That's what gives me this first value, is that first downward diagonal multiplied. The next one, so it gives me the next value. The next one, so it gives me the next value. But then what I do is I add all of those together. So I'm kind of combining all of those downward diagonals. So when I do the diagonals, it's multiplication. When I combine them into one thing, it's addition. All right. The next thing, when I do these upward diagonals, sorry about that, went a little too far. When I do these upward diagonals, once again, I do these 3 diagonals. When I do the diagonal, it's multiplication, which is right here. When I do the diagonal, it's multiplication, but now I add those together. And then just like I did in the previous example, I end up subtracting the upward diagonals combined and the downward diagonals combined, okay? And this is typical. Like the 2x2 matrix is a little bit unique in that we don't do all of those starting values for our downward diagonals. And the reason for that is you could try it doing all of them, but it'll always give you 0. It's a real mess. So we have to kind of do this one each. So I start with each of those first top values into a diagonal, each of the those first bottom values into a diagonal. I add the upwards, I add the downwards, and then I subtract the two. Okay, and this looks complicated, but when we put it into practice, it's really not that bad. So when I look at this guy, again, if I kind of put this into practice, the first thing I'm going to do, and again, what I want here is the determinant of this. I should have determinant written here. And so I want the determinant of this particular matrix. And so the first thing I would do is let's just rewrite these first couple rows. And when it's a 3x3 matrix, you just need to write those first two columns again. All right, so if I write those first two columns again, now it's a little bit easier to see these diagonals. So here's my 3 downward diagonals, okay? So those are my 3 downward diagonals that I'm going to multiply out. You get rid of those for a second. And let's go ahead and multiply them. So when I do this, the first downward diagonal, that gives me a 0. The next downward diagonal that I'm going to add to this thing gives me a -1. The next downward diagonal for this thing gives me a -12. Okay? And now I'm going to do the upward diagonals. We can see that's these 3 right here. So I'm going to do those 3 upward diagonals. And when I do those, again, the first upward diagonal gives me a 0. The next one gives me a 4. And the last one here gives me an 8. And so now what I'm going to do is I'm going to end up subtracting the upward and the downward diagonals. So for this one over here, I get a -13. Over here, I get a 12. And when I do -13 minus 12, that gives me a -25. Okay, so that is the determinant of a 3x3 matrix. Okay, and now here's what we're going to do. We're going to use the determinants to perform Cramer's rule. Okay, and Cramer's rule, again, it's one of those things. It's going to look a little bit complicated, but it's actually a lot easier than what it looks like when we write it out. Okay, in practice, this is a little bit easier. So I'm going to take a linear system of equations, and the thing about determinants is we always want a square determinant for doing determinants. I can't do a determinant with something that's not a square. I need a square matrix in order to be dealing with determinants. And so with a system of equations, we've talked about augmented matrices is when we kind of include the x values, the y values, and what it's equal to all in one matrix. Well, now we're just going to do pieces of this at a time, okay? So the first piece that I look at is just the coefficient matrix. Well, the coefficient matrix is simply just taking this side of the equations and plopping them into a matrix here. I take the x values and the y values and I put them in a matrix. It's really a matrix that's made up the coefficients of x and y, okay? So this is my coefficient matrix, all right? And what Cramer's rule says is this. If I start with that coefficient matrix, all right? So Cramer's rule, let A be the coefficient matrix of the linear equation. If the determinant of A does not equal 0, I can't continue. This thing is not going to work out. I'm not going to have a single solution, an exact solution. If the determinant gives me a 0, I'm going to be in like an all real number situation or no solution type situation. So if there's one solution, then Cramer's rule should give me something other than 0 for the coefficient matrix determinant. And so if the determinant of A is not 0, I can continue. And basically, I can find the system of equations by doing this, okay? I find a couple more determinants, all right? And a lot of times this determinant right here, I'll call it D sub x for the determinant that deals with x. And this guy right here, I'll call it D sub y for the determinant that deals with y, okay? If I find each of those determinants, and we'll talk about where those matrices come from here in a second, and divide them by the determinant from the coefficient matrix, well, it'll give me the actual x value right here. And over here, that'll give me the actual y value for my system of equations, okay? And so the next question is, well, where in the world did those matrices come from? Well, they're simply the coefficient matrix with one of the columns replaced. So like here, when we look at the coefficient matrix up here, if I take this x column right here, all right, and I simply replace that x column with the values that are right here, EF, I get the matrix, the dx matrix that I have written down below. I'm simply replacing the AC column, the X column, with the EF. And then in order to do the Y value, that's this one right here, okay? When I do this Y value matrix, okay, I replace the Y column with this same thing, the E and the F, okay? And so I just replace a column at a time. If I had 3 variables, well, for the X matrix, I would replace the X column with whatever those system of equations equal. Then for the Y matrix, I'd replace the Y column with whatever that system equals. And then I would replace the Z column with whatever that system equals to find the determinants that I need for X, Y, and Z. And so I'm just replacing one column at a time. And once I have those determinants, I simply divide to get the solution for X and Y, okay? So let's take a look at something like this. Again, I'm going to start with just the regular old determinant for the coefficient matrix, okay? So I'm just going to call it D for now and say, hey, that's going to be the determinant of the coefficient matrix. And so for this one, I want the coefficient matrix that's 8, 5, 2, and -4. It's just my coefficients, and I'm going to find the determinant of that. So I do my downward diagonal, that's a -32. I do my upward diagonal, which is a 10, and now I subtract those, which is a -42, okay? So that's my coefficient matrix. Well, now I have to do a matrix that involves X. And so D sub X, I'm going to call it. I'm going to say, oh, well, that's going to represent the determinant of, well, it's like the same old coefficient matrix. Let me just start with the coefficient matrix. But then instead of taking this whole thing, I'm basically going to wipe out this column right here. I'm going to replace this 8 and this 2 with a 2. Sorry, that's with a 2. There we go. We can see that. And a -10. Okay. I simply replace that first column, that X column, with the values that are written right here, the 2, -10. Okay. Let me clean that up a little bit. That looks okay. But just to kind of give you the idea of what we're doing here, we're simply starting with that same matrix, and we're replacing that first column with the 2, -10. Okay. And now I find the determinant. So I find the determinant here. Let's see, that's going to be a -8 and a -50. And I subtract the 2. That gives me a positive 42. All right. And before I actually find X and Y, let me do the last matrix here. This is the dy. Again, that's going to be the determinant of the Y matrix. Just to give you the visual, let me start by writing down the coefficient matrix. And now I simply want to replace those Y column right here. I'm going to replace this with this guy, with the 2, -10, okay? So 2, -10 gets replaced in the Y column this time, and I find the determinant. So if this one looks like I get a -80, a +4, and then I subtract the 2, which is a -84, okay? And so now what Cramer's rule tells me is I can find the X value simply by taking this X value determinant, which is 42, and dividing it by the coefficient matrix determinant, which is the -42. So I find out that the X value here is a -1. The Y value, I simply take this, the determinant from the Y matrix here, which is the -84, and I divide it by the coefficient matrix, which is the -42, and that gives me a +2. And so now I know this system of equations, when I solve it, it's going to give me an X value -1, a Y value of 2, which is the ordered pair -1, 2, okay? And the fact of the matter is we could have easily solved this one by elimination. And if you solve this one by substitution or elimination, probably elimination for this one, if I solve this by elimination, I'm going to get -1, 2 as my answer, okay? This is just giving me another option. You might be looking at this going, well, I feel like that was maybe more work than substitution or elimination. But remember, when we get to bigger equations, like 3 equations and 3 variables, the amount of work when we solve algebraically by substitution or elimination really increases a lot when I go from 2 equations and 2 variables to 3 equations and 3 variables, okay? The amount of work and how much the work increases when you solve it by Cramer's rule, it only increases the amount of work by a little bit rather than kind of increasing the amount of work exponentially, okay? And so the idea here is this: when we get to more equations and more variables, Cramer's rule becomes the better option over something like solving algebraically as we get to 4 equations and 4 variables, 5 equations and 5 variables, okay? Because the amount of work we do, the increase in work, isn't as drastic when we increase the number of equations and variables. It's not as drastic for Cramer's rule as it is for something like our algebraic methods of substitution elimination. Okay. So let's see what this looks like for 3 equations and 3 variables, okay? So once again, this looks very intimidating. However, it's simply the coefficient matrix. If you think about the coefficient matrix for this particular one, the coefficient matrix would be A, B, C, D, E, F, G, H, I. Okay, so that's the coefficient matrix. Well, this first one, this D of X matrix that I call it, is the same as the coefficient matrix, except we've replaced this first column with JKL. And this second one right here, the D sub Y matrix, is simply the coefficient matrix, is the same matrix as up here, except I've replaced this middle column, the BEH, with JKL. And this third one right here, this D sub Z matrix, as I call it, is simply the coefficient matrix again, except with this third column, the CFI column, is replaced with, you guessed it, the JKL. Okay? And so the first time we do this, yes, it's a little awkward, it's a little weird. It looks scary when we see this huge matrix divided by the determinant of the coefficient matrix. But really, those matrices are not that difficult to construct and not that difficult to find the determinant of. Okay? And so for this particular example, let me look at this guy. Okay, the first thing I want to do is I want to set up the coefficient matrix. Okay, so I'm going to do the coefficient matrix, then the X matrix, then the Y matrix, then the Z matrix. Okay, and so the first one, I'm going to call it D. All right, I'm going to let that represent. I'm going to do the determinant of the coefficient matrix. And so the coefficient matrix here is just my coefficients: 1, 2, 1, 1, 1, 1. And this one, a little bit tricky. It's 5, 0, negative 2, because that third equation is missing the y, so I do need a 0 in its place, okay? And again, to make this easier on myself, just copy those first couple columns over here. And again, for a system of 3 equations, 3 variables, when you have a 3 by 3 matrix, you just need those first 2 columns copied over. And now I start multiplying my diagonals. Again, when I do this, I'm doing this diagonal right here, then this one, then this one. I have to write out those 3 diagonals. And so for that first one, I guess I'll keep doing them in green here. That gives me a negative 2, then a 10, and then a 0. Okay, and I'm adding all those downward diagonals together. Likewise, I do the upward diagonals. That's this one, and this one. So I'm going to multiply, get those 3 values. And again, when I multiply those 3 values, I'm simply going to add those together. It looks like a 5, 0, and a negative 4. And then I'm going to subtract these things, okay? And so I'm simplifying this. Looks like that gives me, over here I get an 8. Over here I get a 1. And so when I subtract those, it looks like the determinant here is going to give me a 7. All right? And then I'm just going to do the x next. So I'm going to do d sub x, which I'm going to call the determinant of the same matrix, okay? Really the same matrix here, except instead of having that x column as 1, 1, 5, I'm simply going to replace that x column. Now let me write the x column of 1, 1, 5. I'm simply going to replace this x column with 9, 3, negative 1. And now once again, I'm going to do the determinant. And as a nice little easy way to help me do this, I'm going to write out these values, okay? And so once again, I do the downward diagonals. I'm not going to keep highlighting things, okay? We should get it by now. Negative 18 plus a negative 2 plus a 0. And then I'm going to subtract the upward diagonals. Looks like a negative 1, 0, and a negative 12. And so that gives me a negative 20 minus a negative 13, which is going to be a negative 7. I move on to the d sub y, the y matrix, which again is going to be the determinant of. Same matrix once again, except this time I'm going to replace the y column with that 9, 3, negative 1. Okay, so it's really, I'm just copying the coefficient matrix over and over again, and I'm replacing one column at a time. And again, I do my downward diagonals, -6, 45, -1. I do my upward diagonals, 15, -1, -18. And I do my addition and subtraction, and that gives me a 42. And now I'm going to do the same thing for z, okay? So my z matrix is going to be the determinant of, once again, it is the same 1, 1, 5, 2, 1, 0. But then this last column, instead of being the 1, 1, -2, I'm going to replace with the 9, 3, -1. Okay. And again, to make it easier for myself, to make it easier to multiply out this determinant, I'm going to write those first two columns again. Okay. And so for this one, I get a -1 plus 30 plus 0 minus upward diagonals 45, 0, -2. And now I do my addition and subtraction, and I get a -14. Okay. And so now that I have all of these, I simply go back and say, okay, to find the x value, I take the value I got here divided by the coefficient matrix. And so my x value is going to be a -1. I can write that down here. Let's see, x equals, let's see, that was, which one was which? It was a -7 divided by 7, which is a -1. And next for the y, I do the 42 that I got from that matrix divided by the coefficient matrix determinant, and that gives me a 6. And then for the z, I take the value that I got from the determinant of the z matrix divided by the determinant of the coefficient matrix, and I get a -2. Okay. And so for this particular answer, it looks like it's the ordered triple, -1, 6, -2. Okay. So that's Cramer's rule. Okay. Cramer's rule, we're using determinants of matrices in order to solve systems of equations. And again, it looks like a lot of work, but the nice thing is the work is always consistent. There's no guesswork involved in terms of what steps should I take to move forward. The steps are always laid out. And the amount of increase in work is not as drastic as I get to more equations and more variables. When I get to 4 equations and 4 variables, the work doesn't increase that much for this method like it would for substitution or elimination. Okay.